Okay, let's continue our review of the infrastructure part of the Anchor exam. These are the topics that we have covered so far. Let's go now for the second part of 2.2.b, which is IPSEC. This is actually my second take on IPSEC. I had to erase the previous session because I have reordered the topics and I have split this IPSEC series session into several sessions. Let's go for the first one. Let's talk about an introduction to IPSEC. First of all, what is IPSEC? IPSEC is considered to be a framework. It is not a single monolithic protocol. It is actually a set of many protocols, mechanisms, or procedures, and mainly uses several cryptography algorithms. These cryptography algorithms evolve over time, and as these cryptography algorithms evolve, so the RFCs that define IPSEC also change and propose or recommend the use of the more recent generation of cryptography algorithms. The basic definition of IPSEC can be found in the ISACAM RFC. We have two versions of IPSEC mainly out there. IQ version 1, which is no longer in use, and IQ version 2. IQ version 2 is more secure, is faster. So if you see devices that are configured with IQ version 1, you should migrate them to IQ version 2. IPSEC is based on two phases. Phase 1, that is known as the control plane, and phase 2, which is known as the data plane. So keep that in mind, that IPSEC uses two phases. Now, why do we need IPSEC at all? Because the original set of TCP/IP protocols were created without security in mind. So we are going to add security to the IP protocol with IPSEC. What security features are we adding? Integrity, authentication, confidentiality, and anti-replay mechanisms. So let's go for integrity first. What we are going to accomplish with integrity is making sure that packets arrive unchanged. So when we send a packet over a transport network, there is the possibility that a third party changes the packet. So when the packet arrives into the destination, we need a way to tell whether this packet was changed or not. So we are going to use a hashing algorithm for this. When we read the term hash, we need to immediately think of integrity. What these hashing algorithms do is reading the contents of a packet, then apply a set of mathematical functions and come up with a number. We are going to store this number into a new header field. Let's call it integrity check value. Now, when packets arrive into the destination device is going to execute the same hashing algorithm. So we are going to read the contents of the packet, we are going to apply the same set of mathematical functions, and we are going to come up with a new calculated number. If the new calculated number matches the content of the integrity check value, then we are going to reach the conclusion that this packet was not changed on the transport network. Otherwise, we are going to drop the packet. This is the basic mechanisms of integrity. Now, there are several hashing algorithms out there. We have old algorithms out there. For instance, message digest 5 or secure hashing algorithm 1. We should not use these ones because they are breakable. We have the set of SHA-2 algorithms that are more recent. You can use them. And we have a new generation of hashing algorithms that we are going to talk later on. Okay, let's talk about authentication. By authentication, we are going to make sure a PID is who it claims to be. So we can have, for instance, this blue router that receives a request to establish communication with a remote peer that claims to be, in this case, the yellow router. So we need a way to make sure that the remote peer is who it claims to be. So we can have a legitimate peer that happens to claim to be also, in this case, to be the yellow router. So we can have a rogue device claiming to be the yellow router, and we can have a legitimate device claiming to be the yellow router. So with authentication, we are going to make sure a peer is who it claims to be. There are several authentication methods here out there. The most easy one to deploy is known as pre-shared key, or PSK. With PSK, we're going to go into every single one of our routers, and we are going to manually configure a key. This key must match in order to authenticate devices. So a third party will not know this key, so it will not be able to authenticate. It is easy to deploy. It is not as secure as other methods because over time the third party can guess the key. So you must use a hard to guess key, and you should change it over time as best practice. So all devices must know the key. There are two options here. We can use symmetric keys. That means that we are using the same keys on all devices, or we can use asymmetric PSK, where devices can use different keys. There is other authentication methods. For instance, we can have signed certificates. In order to have signed certificates running on our network, we need a third device that is known as a certificate authority. And this certificate authority device can be a Windows device, a Windows server, or a firewall, or a Cisco device with the appropriate set of commands to become a certificate authority. And the way it works is the following. You are going to create an unsigned certificate on your device. This unsigned certificate is going to borrow some information from this particular device in order to be created. For instance, the host name or the IP address of the device. Then you're going to take this unsigned certificate to your certificate authority. Your certificate authority is going to sign it. Then you're going to take this signed certificate back to your device, and you're going to install this. The same procedure applies for every single device in your network. You are going to create an unsigned certificate. This unsigned certificate is going to borrow some information from this particular device, for instance, the host name or the IP address. You are going to take this unsigned certificate to your certificate authority. The certificate authority is going to sign it, and then you're going to take back this signed certificate to your device and install it. So a third party will not be able to have a signed certificate because the third party is actually not having access to your certificate authority. So in that way, only devices having a valid signed certificate will be authenticated to each other. So this process is more secure, for instance, than pre-shared keys. It is harder to deploy. You need a certificate authority. Your certificates will expire usually after 1 year. So you have to make sure to refresh your certificates. If you change certain parameters on your device that were used to create your certificates, you're going to break your certificates. For instance, if you change your host name and your host name was used in order to create your original unsigned certificate, you're going to break your signed certificate. So in summary, this is harder to deploy than PSK. Now, we have new ways to perform authentication. These are only available for the recent version of IPSEC, known as IKEY version 2. We can use asymmetric pre-shared keys. We can use extensible authentication protocol now, so we can use a radius server to perform authentication, or we can use elliptic curve digital signature algorithms, only available for IQ version 2. These are considered now to be old ways to authenticate, symmetric PSK or signed certificates. Okay, let's talk now about confidentiality. With confidentiality, we're going to avoid sending data on the clear. That means that we are going to avoid third parties from accessing the data within the packets. In order to do so, we are going to perform encryption. There are several encryption methods out there. We have, for instance, these old encryption methods, data encryption standard or triple DS that you should not use because they are breakable. We have a more recent encryption methods, for instance, advanced encryption standard 128, 192, or 256, and we have the new generation of encryption standards. Notice that you can also choose not to encrypt data. That is also a valid option for IPSEC. It is defined in this RFC, so you can choose not to encrypt data if you want. Coming back to this new generation set of encryption algorithms, we have Galois counter mode. This particular algorithm can perform encryption and can perform hashing. It can perform two functions. We have cipher blockchaining, and we have, for instance, Galois message authentication code. This particular algorithm also claims to do encryption and hashing, but the encryption that it's performing is null encryption. So it is actually not performing encryption, it is actually only doing hashing. Now, in order for these encryption algorithms to work, we need two other things. We need to create keys and we need to exchange these keys. So in order to have encryption algorithms working, they need a secure way to create keys and share key material over the network. And in order to do so, we use Diffie-Hellman. So Diffie-Hellman is a protocol that is an algorithm that creates keys, and it is a protocol that exchanges keys. So we have two sets of Diffie-Hellman algorithms. Diffie-Hellman algorithms are identified by a group number. We have what we consider to be the old set of group numbers for Diffie-Hellman that are based on mod P or modular exponentiation, group 1, 2, 5, 14, 15, and 16. You should not use these ones because they are breakable. Make sure to use Diffie-Hellman groups that use more than 2048 bits. We have the new generation of Diffie-Hellman algorithms that are based on elliptic curve or ECDH, Diffie-Hellman, group 19, 20, and 21. And we have also a new generation of exponential Diffie-Hellman, group 24, for instance. Let's talk now about anti-replay mechanisms. Anti-replay means making sure that copies of packets cannot be sent again. So let's say, for instance, that this blue router is sending this particular packet to the yellow router that includes authentication information. Now, a third party is not able to read the contents of this packet because we are encrypting this packet. But what this third party can do is copy this packet. So this party can send this packet later on, and if this, in this example, this packet happens to be an authentication packet, there is the possibility that this third party can authenticate itself to this device using the copy of a packet. So anti-replay mechanisms are based on using what we call sequence number. So let's say that we add a new header field that we are going to call the sequence check number. And we are going to assign this header field with a value, let's say 1. So this value can only be acceptable by the destination on a receive window. So only for a certain amount of time, this packet that happens to have this sequence number will be allowed to be received. If this third party copies this packet will be sent later on with the same sequence check number, and the window for this sequence check number most probably will end by the time this packet is sent again. So this packet will be dropped because it arrived once the window was closed for this particular sequence check number. Now, this is a summary for what we saw. Remember, for authentication, we have these old methods. We have these more recent methods to authenticate that are only available for IQ version 2. We have these hashing algorithms that we should not use. They are old and breakable. We have this other set of recent hashing algorithms that we should use, which are the SHA-2 set of algorithms. But we can also use the new generation of encryption protocols that do encryption and hashing. So in this case, GCM and GMAC do encryption and hashing. So we can use it, but only for phase 2 for IPSEC. Remember that IPSEC uses phase 1 and phase 2. So these are available only for phase 2. Regarding encryption, we have an old set of encryption algorithms that we should not use, a more recent set of encryption algorithms that we can use, and we have the new generation of algorithms. Remember that GCM is only available for phase 2. It can perform hashing as well as GMAC. Remember that we can also use null encryption. It is also available for phase 2. In this case, GMAC is a new generation of algorithms that does not perform encryption but can do hashing. And we can use CBC, which is also a new generation of encryption algorithms that can only do encryption. We also talk about Diffie-Hellman, which is a way to create key material and exchange keys. We have an old set of Diffie-Hellman groups. We should not use 1, 2, or 5. We can use 14, 15, and 16. And we have a new generation of Diffie-Hellman algorithms, elliptic curve, and exponential. Now let's compare an old version of the IOs with a more recent version of an IOs. For instance, with traditional IOs, in this case we have an iOS that happens to be version 12.4, which is a bit old. So let's see what options we had back in the day for IPSEC. So let's see, for IQ version 1, phase 1, we have these encryption algorithms. We had these hashing algorithms. We had these Diffie-Hellman groups. And we had these authentication methods. Now, for IQ version 2 phase 1, we actually didn't have IQ version 2. Now let's compare that with a more recent version of the iOS, in this case iOS XE16. Let's see what we have for phase 1. This is for IQ version 1, phase 1. We now have these encryption algorithms. We now have these SHA-2 hashing algorithms. We have more recent Diffie-Hellmans or new generation of Diffie-Hellman groups. And the authentication is the same because this is still old IQ version 1. Now for IQ version 2, we have these encryption algorithms, new generation of encryption algorithms. Hashing and Diffie-Hellman groups. Elliptic and exponential. Now for phase 2, with the old IUs, we had only triple DES and AES for encryption, and MD5 and SHA for hashing. Now, for phase 2, with the recent IUs, we have new generation of algorithms with more recent hashing options. Now, the authentication for IQ version 2, we have these new methods. Instead of authentication protocol, that will be asymmetric pre-shared key or ECDSA or signed certificates. That's it.